Today we'll be doing 8.5, which is on systems of inequalities. So we'll graph them, we'll graph a nonlinear one, use mathematical models involving those, and then graph a system of inequalities. So equations in this form are straight lines when they're graphed, but we can change the equal sign to a less than, a greater than, less than, greater than or equal to, and less than or equal to, and that will turn it into an inequality. So the solution of an inequality is an ordered pair of real numbers where the x-coordinate is substituted for x and the y-coordinate is substituted for y, and you would get a true statement. So the ordered pair would be satisfying the inequality. The graph of the inequality is the set of all points whose coordinates satisfy the inequality. So you'll end up with a shaded region. Anything in that shaded area is going to make the inequality true. So if it was just a linear system, it would just be a straight line, and anything on the line would make it true. But this time it's anything above or below the line in the shaded area would make it true. There's a variety of solutions instead of just one. So your first step is going to be replace the inequality symbol with an equal sign so that you can graph it like a normal linear equation. You'll draw a solid line if the original inequality has a less than or equal to or greater than or equal to, because you could include the numbers on the line. You'll draw a dashed or dotted line if the inequality has a less than or greater than symbol, because it could not be anything on the line, but it could be anything above or below it depending on where the shaded area is. Then you'll choose a test point from either the shaded area or above the line or below the line to decide if that coordinate should be included. If it should be included, then you'll shade that section. So if a true statement results, you'll shade the area that includes that test point. If it's false, then you'll shade the opposite area, the one not containing the test point. So we'll go ahead and look at an example here. So first we have 2x minus 3y is greater than or equal to 6. And I forgot to change this equation to match that. So let me change that to 2x minus 3y. And we're going to change this to an equal sign because we could figure out how to graph that if it was an equal sign, and then we'll just try to apply it to an inequality as well. So one way to do this is to change it into slope-intercept form. Another way is to find the x-intercept and the y-intercept. So to find the x-intercept, you want to know when the y is 0. That will tell you where it hits the x-axis. So I'll go ahead and replace the y with a 0. So that just leaves us with 2x equals 6. So the x is 3 when the y is 0. So that is our x-intercept. And our y-intercept is when the x is 0. So we'd have negative 3y equals 6. Divide by negative 3. And you get y equals negative 2. So when the x is 0, the y is negative 2, and that gives us the y-intercept. Then we'll be able to put those on a coordinate plane to help us graph. Okay, so for this one, the x-intercept was 3. And the y-intercept was negative 2 for ours. Okay, so now let me go ahead and find that. So the x-intercept was 3, so it's going to cross the x-axis at 3. And the y-intercept was negative 2, so it crosses the y-axis at negative 2. And now we have to look back at this symbol. It said greater than or equal to, so it's going to be a solid line, as straight as you can make it. It's kind of hard on an iPad to do that. So now I have made a line. You can make it go farther. If I had a ruler, I would make it go farther, but it's hard to make a straight line on here. So we have a solid line, meaning anything on the line would make this true. Okay, now we're going to choose a test point. So let me go ahead and plot our intercepts again. The x-intercept was 3, the y-intercept was -2. And then we had a solid line going through those. So whenever you can test the origin, you're going to want to do that. So usually you can do that unless it goes through the actual origin, but the line does not. So let's go ahead and test this point. We want to know, would that point be part of the solution set or not? So here was our original inequality. So we want to know if we replace the x and the y with 0, is this true or not? Let's go ahead and try it. Is this true? So we'd have 0 minus 0, which is 0. Is that greater than or equal to 6? No, that is false. So we don't include 0, 0. So that means we would only have the solutions that are below this line. So I like to use colored pencils or highlighters, and that's why it's good if you can extend this line all the way to the edge of the coordinate plane if you have a ruler, so that you have a true, right now I'm just kind of estimating where it would end and begin. But anything in this yellow is going to make this true. And again, that 0, 0 coordinate should not be included, so that's why I shaded below it. Okay, so this was just another one if you needed more room, but I already did the shading on the last one. So if you needed more room, you could have put it on this coordinate plane instead. Okay, and then I put another step-by-step example you can look at. Here's the intercepts. Then they tested 0, 0 and got something false again, because 0 is not greater than or equal to 8. So they're going to shade below the line. Because they do not want to include 0, 0. Okay, now this one, instead of using intercepts, we have something that's already in slope-intercept form. So let's review. Slope-intercept form is y equals mx plus b. This is the slope. This is the y-intercept. So on this one, there's nothing behind it, but you could put a plus 0. So that means my slope is -2/3, and that's the rise over the run, how far it goes up compared to how far it goes over. Then the y-intercept equals 0. So this one, I'm going to graph the y-intercept at 0. And then I'm going to go -2, so down 2, forward 3. I'll do that a couple more times. Down 2, forward 3. You could also go up 2 and then back 3, as long as the negative is either on the top or the bottom. Okay, this one is going to need to be a dotted line because it does not have the equal to symbol under it. So do your best to make a dotted line or a dashed line. Okay, now this one we cannot test 0, 0 because the line goes through it. So we're going to have to test something above the line or below the line. I'll do that on the next slide. Okay, so again, this one we cannot use 0, 0. Let me go ahead and put the line on here again. We start at the origin, went down 2, forward 3, or up 2, back 3. So there's a dashed or dotted line. So let's try to think of something that would be easy to test. So maybe right here. That'd be a good point, an easy point to test, 1, 1. So test the origin if you can, but if it falls on the line, then you're going to have to choose something different. So here was our inequality. So I'm going to replace the x and the y with 1s and see if I get a true statement. Okay, so is 1 greater than negative 2/3? Yes, this is true. So do include 1, 1. So that means we want to shade wherever the 1, 1 is at. So that's my red dot, so I'm going to go ahead and shade that area. It's going to be everything above that dotted line. So I could pick any point. I could test this point here, it should be true. This point here should make it true. Anything in between as decimals and fractions, anything in that yellow is going to make this inequality true. Okay, now we're looking at a nonlinear inequality. So if you remember our circle formula, it was x minus h squared plus y minus k squared equals r squared. And hk is the center. So on this one, the center is just going to be 0, 0. And then the radius had to be squared, so that means this would have been a 4 squared. So the radius is 4, so they counted out to 4 in all the directions. And we're going to make a solid circle because we had an equal to sign under the symbol. So this one we will test 0, 0 because that's an easy point that's not falling on the circle. So you can see that when we replace those, we get a false statement. So we do not include 0, 0. So that means you're going to shade everything on the outside of the circle. Anything outside the circle is going to make this statement true. Anything inside is going to make it false. And there's just another visual. That is the shaded area. Okay, an application problem here. So this is the latest guidelines which apply to both men and women, give healthy weight ranges rather than specific weights for your height. If x represents height in inches and y represents weight in pounds, the healthy weight region can be modeled by this system. And we want to show that this point is going to be a solution to the system. And we said x was height, so this would be the height, and this would be the weight. So someone is 66 inches, we're saying 130 pounds should be in that healthy weight range. Okay, so on this one, we're going to plug in both of these into each inequality and see if we get a true statement. So we went ahead and replaced the x with a 66 and a y with a 130. And then we did the same here. Replace that with 66 and this with 130. And you end up getting a true statement at the end of both. So therefore, this point does satisfy both inequalities, so it would be a solution for the system. Okay, so the solution set of a system of linear inequalities in two variables is a set of all ordered pairs that satisfy each inequality in the system. So to graph a system of inequalities, we're going to begin by graphing each individual inequality in the same coordinate system. Then we'll find the region, if there is one, that is common to both. Or there could be more than two. This region of intersection gives a picture of the solution set. Okay, so this time we're going to have two inequalities that we have to graph together and then see where the shaded areas intersect. So step one is to replace the inequality symbol with an equal sign and graph both of them. And again, you could do this by finding x and y intercepts or rearrange into slope-intercept form. So I'll do the x and y intercept method. So we'll change the first one to an equal sign, change the second one to an equal sign so that we can create a graph for them. So the x-intercept, we're going to replace the y with 0. So that's just x equals, sorry, that should have been a 1 right here. So x equals 1 when y is 0. So our coordinate is 1, 0 there. And then our y-intercept, again, this should be a 1, is when the x is 0. So that's negative y equals 1. So if you divide by the negative, that's like a negative 1. You get y equals negative 1. So the y-intercept when x is 0 is negative 1. So those are our two intercepts for that one. Now I'll do the same process for this one. So I'll start by replacing the y with 0 to find my x-intercept. So the x is 6. So 6, 0 is our x-intercept. Now to find the y-intercept, replace the x with 0. Divide by 3. So y equals 4 when x is 0. And then we'll graph those on the next slide. Okay, so our first the intercepts for the first equation were 1, 0, and 0, negative 1. And the line is going to be dashed because it started as a less than sign. So it's going to be dashed because there's no equal to sign. So there's 1, 0, and then 0, negative 1. Make a dashed line. And then our other intercepts were 6, 0, and 0, 4. And that line is solid because it was 2x plus 3y is greater than or equal to 12. So it had the equal to sign, so it is going to be a closed. So solid line, straight as you can make it. Okay, so now we're going to do our testing. So let me go ahead and plot those points again. I had these with a dotted line. And we had a solid line for the other one. Okay, so let's look at our first one. We're going to test 0, 0, see if it's true or false. So 0 minus 0 less than 1. Yes, that is true. So I'm going to include 0, 0. And this was for my dotted line, so I'm going to shade everything above. And now let's test the blue line. That was 2x plus 3y is greater than or equal to 12. And we're also going to test 0, 0 because that does not fall on the line. So that's just 0 plus 0, which is 0, is greater than or equal to 12. Is that true? No, that is false. So therefore, I should not include 0, 0. So that 0, 0 should not be included this time. So this is why I like to use different colors. So now I'm going to use a green highlighter. I cannot include that red dot. Let's make it green so you can see a little better. I'm not going to include the 0, 0. So I need to shade where that does not fall, which is above. So if you had color pencils or real highlighters, it would have changed this blue because you could have had an area where it would have intersected and you would have been able to see this a little better. So let me go ahead and in black, let's do red actually. This area here is what they both have in common, and you'd be able to see that a little better if your line went all the way out. So let me extend that. So the red area is what makes both true. So anything in that red area makes both inequalities true. And again, it could keep going. Just has to be in this little triangular section. And then there's another step 1. And you would end up seeing a shaded area. They don't have it printed here, but you could shade the two areas and then see where they intersect. Wherever they intersect is what makes both of them true.